Okay, kids, it's time for lesson 3, which is about inscribed angles in a circle. This might be one of the most surprising things you've ever heard about circles as we get into this unit. So here we go. An inscribed angle has its vertex on the circle and sides are chords of the circle. An intercepted arc has endpoints on the sides. Okay, this is a lot of really technical language. Let me just show you what that means. So I've got it all lined up here in GSP. This thing here is called the intercepted arc. This bold part of the circle here. The inscribed angle is this thing over here. It's the angle where the vertex is on the circle, and notice how this angle has inside it this arc here. Okay, as you see in this picture in the theorem. Okay, so it's saying that if you've got an angle where the vertex is on the circle and it's kind of like it's eating this angle here, I don't know if you can see it, but it's also a different color, just like mine was in GSP. The measure of the angle equals 1/2 the measure of the intercepted arc. This is kind of, like I said, new and surprising. So what's going on here is I've taken the measure of this arc over here. It's 112 degrees, and of course I can change it, and that's fun. So let me make it 110 just for simplicity here. And then notice the angle over here at D, where the angle kind of goes through the circle right here, where this is the intercepted arc. The measure of this angle is exactly half. I did a little division there so you can see that, but it's kind of crazy because it doesn't matter where this is on the circle. This angle stays the same. I can even kind of go over here. Notice it's always 55 degrees no matter where I move that, as long as it's intercepting an arc of 110. All right, this is also saying, by extension, kind of, that if you had two angles that were both intercepting the same arc, they would, of course, have the same measure, because they're both half of this intercepted arc. Let's see that over on GSP. All right, so I just made another angle here that's almost right on top of that one, but I think if you see that if we can move this, it stays the same angle. Well, then if ever I have two of them that are intercepting the same arc, this angle and this angle, of course, they're both going to be the same measure. So if you ever see a picture, like a static picture like this, where two of the angles are both intercepting the same arc, they're going to remain congruent because they're both, like, of course, half of this angle. Of course, I can change that. That's kind of fun. So this angle, the angle at D and the angle at E will be the same measurement. I have this dotted thing drawn here at A just to show you that that's, remember, how we measured this arc in the first place. This arc and this angle will have to be the same. Another interesting extension of this, if the intercepted arc happens to hit the circle at the ends of a diameter, well, then that angle is going to have to be exactly 90. Let me show you why. So here we are back in GSP. If I move this arc around so it's exactly half of the circle, so this is really close to 180. I don't know if I can get it perfect, but I'll get close. Then this angle is going to have to be 90, because now the intercepted arc, the arc that's inside that angle, is a semicircle, so it's going to be 180. And again, I'm really close. I'm not exactly there. If I make it 180, then this is going to have to be 90. And lastly, if I have a quadrilateral inscribed in a circle, the opposite angles of that quadrilateral are going to have to be supplementary. And let's see why. All right, so here I've drawn a quadrilateral in a circle, and I mean inscribed in a circle, where all the vertices are on the circle. And I've colored this here so that the orange angle is intercepting the orange arc, and the blue angle is intercepting the blue arc. And notice those two arcs together make up the entire circle. I've measured them, and I've shown the sum down here. Those two arcs have to be adding up to 360. And the blue one, remember, is going to be half the degree measure of the blue arc, and the orange one's going to be half the degree measure of the orange arc. So guess what? Those angles have to add up to 360. And of course, I can move these around. No matter how crazy this quadrilateral looks, the opposite angles, here that'd be angle B and angle D, have to add up to 180. And that would be true no matter what I do here. And it's also true of angle A and angle C. If I was to do this kind of sideways, I could measure angle A and angle C, and those would also have to add up to 180. All right, so let's see all of those things in action here. We have find this circle here, circle E, find measure of angle ABC. That should have a little m in front of it. And measure of angle ABC and x. Well, if this is 20, our first rule says the angle here, if it rests on the circle, if the vertex is on the circle, it's half of the arc that it intercepts, and this arc is the arc that it intercepts, so this one has to be 40, because that angle should be half. By a similar token, if I see a 110 here, any angle that intercepts this arc that's on the circle is going to have to be half of that, so this is 55. What am I looking for? ABC, ABC, okay, I'm getting close. Oh, this 40 here, This is intercepted by this 20 here at C, but it's also intercepted up here at this angle at B, so I also know this is 20, and I think that's all I need to be able to find ABC. ABC is then going to be 75. Finding X, Y, and Z in this circle, we have this 51 up here at G. The arc that's inside that angle is down here, so this has to be 102. I'll just write it right there because I'm out of space on the outside. This 27 shows me that the arc inside that has to be double, so this is 54. What else do I know? Oh, that 54 is also intercepted by this X down here, so this is 27. I guess I could have known that just knowing that both these angles both intercept GC. The thing I find interesting about this unit is that a lot of times in these diagrams of circles, the answer that you're seeking is found completely on the other side of the diagram, and it's kind of surprising sometimes. Like, I'm trying to find this angle Z, so I start looking in this triangle, and I don't see anything there. Well, the answer to how I find angle Z is actually because, you know, it's actually found over here, because angle Z is pointing at this arc way over here in this part of the picture. And if this is the center of the circle, I know CF is a diameter, so this entire thing here has to be a diameter. So that adds up to 180. So this arc from G to F has to be, oh, let me do this in my head, 146, I believe. Oh, I think I did that wrong. Yes, it's 126. I did that really wrong. Okay, so that's 126. This angle right here has to be half of that, which is 63. Another way I might have known this was 63, that rule we just found out about the diameter, I know this thing has to be a right angle, and knowing that I have a right triangle here and there's a 27 here, this has to be 63 to make 90, so that would have worked. And if this is 51 in a right triangle, in a right angle, this has to be 39, and I think that's everything I need. All right, next one, find X and Y. Again, I have a diameter, dA. If dA is a diameter, then I know these guys are 90. That's kind of helpful. This is X and this is 80. Well, that means that, you know, since this is the intercepted arc here for this angle, this is 40. This appears to be a kite with those things being the same. So I have congruent triangles here. That's also 40. I have a right triangle with a 40 in it. The other angle must be 50 to make 180 in that triangle. Okay, points of tangency. Oh, we didn't talk about this in GSP. Let me show you something. Back to this demonstration in GSP. The book didn't do a great job of explaining this, but I can extend these angles. I've made these angles into rays now, so you can see kind of more of this angle. And of course, we talked about how this is always half of the intercepted arc. What if I were to put this point D right on C? Notice how as I get closer and closer to C, notice the angle isn't changing sides. It's still the same size over here. It's still half of the measure of the arc. Turns out that if it's actually tangent, and GSP won't let me do it, if I put it right on there, it's going to kind of flip back and forth and it's not going to know what's happening. But you can probably imagine if it were right on there, it's still going to stay the same size. It's still exactly half of the intercepted arc. So back in here, I know that things like Y are going to be half of arc AB, and X is half of arc AC. Now that we know that, I think we can go a little further here. All right. Well, first of all, this 140 is a kind of an older example. I'm used to that one. So this is half of the 140. I have a triangle ABC, of course. So this has to be 50. And then for finding X and Y, I need to know more about the rest of the arcs in the circle. Well, if this is 60, it points at this arc over here that's 120, and if angle C is 50, it points at this arc over here, which is 100. And so now I can tell that Y will be 50 because it's half of 100, and X is 60 because it's half of 120. All right, here's the quadrilateral rule, of course. Opposite angles in a quadrilateral are going to have to be supplementary, so it tells me Y and 68 add up to 180, so this is 112. X opens up to this huge arc here at DE. I don't really know if know what CE is yet because I don't know. It looks like DE is a semicircle, but I can't really be sure of that. I know that FE is 94, and so if I had an arc opening up to that, I would know it's half, but I don't really. There's no angle that has C and F just right on one angle. I could connect F and C, and I would know FCE is half of that. But I do have this angle at E that says it's 68. 68 being on the circle tells me that arc CF has to be double of that. So this is 136. Now with 3 arcs of the entire circle, the only thing left is CE. I could figure that out. If I add those 3 up, I know that it's that big. And then to find the rest of the circle, I'll just take 360 minus that, and I find out that the missing arc is 184, or sorry, 84. So with this arc up here being 84 here at CE, I know that the entire arc from D to E is 130. So this whole thing is 130, and this has to be half of 130. So there we are. And lastly, we have this isosceles triangle. What's nice about isosceles triangles is we know that these two angles are the same. So once I find x, I know x and this angle over here are going to be the same. So let me just put an x right here. And also x is half of y. That's kind of nice. X is half of y. This arc will have to be congruent to this arc, because if these angles are congruent, of course they have to point at congruent arcs. Now I've kind of spoken about the whole circle here. I know that there's 32 out here and these other things are equal. So I can calculate what's left if I take 360 minus 32 and divide that by 2. I'll have 164 for each one of those. Sorry, what did I say? 164, okay. So y is 164 in both accounts. And this one, of course, is half of that. So this one's also 164. And these guys are 82. And that's all for this lesson. I will see you later.